This lesson will be video lesson 16.1, the part 1 of chapter 16, which is on acids and bases. We began that and touched on it when we talked about normality in chapter 15. Some things you should know about acids or bases. You probably already do. They are, of course, sour tasting. Now, please don't taste acids, but if you look on Sour Patch Kids or Warheads, you'll see things like citric acid or ascorbic acid. They also react with metals to form hydrogen gas. We know this from the Hindenburg reaction that we did way back in October. If you add metal to hydrochloric acid, you get a salt, zinc chloride, and a whole bunch of very flammable hydrogen gas. Acids will also react with metal carbonates. Okay, remember what the carbonate ion is. CO3 2 minus. Let me go use this. That's much better. CO3 2 minus. So calcium carbonate reacted with hydrochloric acid will produce something different. Notice it produces CO2 and H2O. Just like any neutralization, water is produced. But what's also produced is CO2. So again, look at calcium carbonate, chalk dissolved in H2O. It's going to bubble and fizz because we're producing CO2 gas this time. This reaction at the bottom is something you're familiar with already. This is the vinegar volcano. So notice this is acetic acid, a hydrogen in front, and the acetate ion, and sodium bicarbonate. And that's baking soda. So we've got baking soda and acetic acid, which is vinegar, producing CO2, it bubbles and fizzes, and H2O, liquid water. And then a salt left over. In this case, it's sodium acetate. Bases, on the other hand, have some other properties. Bases are slippery. We sometimes say bases are alkaline. You know, acids are, of course, acidic. Bases are alkaline. You know that some things that are slippery are bases. Soap is a great example. Almost any cleaning fluid like ammonia or bleach are also weak bases. They're good at breaking hydrogen bonds. So they're excellent solvents. We also know that bases come from alkali metals and the alkaline earth metals on the periodic table, because if you take a chunk of sodium or potassium in this case and you throw it in water, you get a base here, potassium hydroxide, the OH minus, and it of course bubbles and fizzes, and you get some hydrogen gas as well. When we study acids and bases and we do experimental stuff, we usually use an indicator. Indicators are substances that change color under different pHs. Now, what is pH? We'll get into that in great detail later, but you can kind of think of it as the power of the hydrogen ion in solution. It's a measure of concentration in moles per liter, sort of, and we'll get into that more later. A common indicator is this thing called phenolphthalein, and phenolphthalein is something that is clear but turns pink in a base. It's clear in notice in acid or when it's neutral. So if this were pH 3, it would still be clear, but in a base it turns pink. That's an important indicator that we might be using in a virtual lab later this year. Another thing about acids and bases is that they are always electrolytes. Remember, they produce ions in solution, so they will carry electricity. Some other indicators that are used are sensitive to different ranges in pH. You can combine them together and make a thing called universal indicator. So this actually contains a number of different chemicals that turn different colors at different pHs. So you can combine them and make a colorimetric pH scale. Here's a weak acid, vinegar, so you can see pH around 3 or 4. Club soda, an even weaker acid, maybe a 5, 4 or a 5. And here's ammonia, again, a weak base, looks like a 9 or a 10, according to that. If you guys have an aquarium, some of you know that fish are quite sensitive to pH. This is an indicator called bromthiamyl blue, and bromthiamyl blue is extremely sensitive to pH changes close to neutral, and fish like it very slightly acidic, and so being too acidic, though, can of course kill fish. Bromthiamyl blue is on this chart. There it is, bromthiamyl blue, right around the the pH neutral range. Let me scroll down here. So what else do we have to worry about? Okay, remember our old operating definition of what is an acid or what is a base. An acid is something that donates hydrogen ion to solution, H+. We're going to refer to that as the proton because remember, that's what it is. It's a hydrogen without its single electron, and its nucleus is just a proton. Bases were things that donate OH minus or the hydroxide ion to solution. So as an example, strontium hydroxide, when this dissolves, is going to produce the OH minus ion in solution. This is oxalic acid. Well, this will produce 2 hydrogens and then the oxalate ion, something else. In solution. Now, the relative amounts of these 2 ions determine whether something is an acid or a base. And we're going to use some new symbology, some new symbols here. This, notice, is an X in brackets, and those brackets have a meaning. What that meaning is, literally translated, this would be the concentration of X in solution in moles per liter. So this right here, you could say the chloride concentration is 0.4 moles per liter. When you see those brackets, you don't even have to write units anymore. It is understood that that is in moles per liter. So notice in an acid, we're going to have more H plus than OH minus. And therefore it's considered an acid. A base is just the opposite. The OH minus is greater than the H plus. And of course, when they're neutral is when they're equal. There's more of neither one nor the other. Now, this is our old school model of acids and bases, and it has a formal name. It's called the Arrhenius model of acids or bases, named after Svante August Arrhenius, a first Swedish chemist to win the Nobel Prize in 1905, I think. You can check my work on that one. So again, any compound that adds H plus is an acid. Anything that adds OH minus is a base. Remember your strong acids and bases. There's your strong acids, hydrochloric, sulfuric, nitric. Here's your strong bases, are just potassium and sodium hydroxides. This is not one you have to remember, but it's just another example of something that donates OH minus to solution. There's vinegar, again, the H plus in front of the acetate ion right here. What that looks like in organic chemistry structure is whoops, let me undo that. Excuse this little glitchy software here. And let's undo. There we go. This is the ion, the H plus ion that ionizes from that molecule. So when that goes into solution, it's created an acid. Now, the problem with this older model is that there are some materials in nature that produce a base, even though they look like they shouldn't. An example of that is ammonia. When you dissolve ammonia in water, you get a basic solution, pH of around 9 or 10. Now, where's the OH minus coming from? Remember, our old definition is a base adds OH minus to solution. So this is falling apart here. What ammonia actually does is kind of interesting. Ammonia reacts with water and splits it apart, actually grabbing the H plus ion from a water, leaving OH minus in solution. So even though there's no OH minus as part of the ammonia molecule, we end up with it in solution, and that's why it's considered a base. This new model is called the Bronsted-Lowry model. We need something new to define how acids and bases work. And the key to the Bronsted-Lowry model is that you focus on what the hydrogen ion is doing, what the proton is doing. An acid is defined pretty much the same way, something that donates H plus to solution. But a base is something different now. A base is not something that donates OH minus, but something that accepts the H plus ion. So here is some new symbology as well. I want you to notice this symbol in the middle here. That's a two-headed arrow. That's a new symbol that we're going to have some phrasing for. We're going to say is in equilibrium with. This is the equilibrium symbol right here. Okay. And what this means is that reactions can go forward, but they can also go in the reverse direction. And another piece of new chemistry is this right here. That is the hydronium ion. Now, normally when this thing would split up, of course we get H plus and we would get some generic anion. That's what this stands for, by the way. It's some acid, it's H plus, and An minus, the anion. But this H plus is something that actually doesn't really exist in nature, especially in water. If there's water nearby, that H plus is going to attach itself to that very polar water, and you end up with this thing. And that thing is called the hydronium ion. That's what really exists in nature. This idea that the H plus ion is floating around in solution isn't really true. It actually exists partially attached via hydrogen bonds to the sorry, that's wrong, via covalent bonds to the water molecule. All right, we're running out of time, so I'm going to close this up soon. So the trick with this new model, the Bronsted-Lowry model, is that it has two directions. It has a forward reaction, and it also has a reverse reaction. So notice in the forward reaction, this material right here, HAN, this generic thing, is the acid, of course, because it's donating H plus in solution. But notice what water does. Water accepts that H plus and becomes H3O plus. So water is acting like a base in this reaction right here. So in the forward reaction, HAN is the acid, as we expect. H2O is a base because it accepts the proton. But there's also a reverse reaction. Let me scroll it right to here. Okay, in the reverse reaction, we have a thing called a conjugate acid. So notice, think about this. In the reverse reaction, we have H3O plus going this direction, back to the left, and donating an H plus because it loses it. It turns back to water. And that H plus goes to the An minus to form the original molecule. So in the reverse direction, water is acting like an acid here. And that's called the conjugate acid. Whenever you see the word conjugate from now on, conjugate, think in the reverse direction. Okay, conjugate means in the reverse direction. And there's also got to be a conjugate base, something that is accepting the proton in the reverse direction. So if you notice right here, here's this thing we've called An minus, some generic anion. In the reverse direction, it accepts a proton and goes back to being HAN, the original acid molecule. So I'm going to stop this here, and we will go into much more detail on this because this is a tricky concept, but this is a good place to end for the day. Well done.